probably at this point have seen a couple of very basic first order circuits, maybe a lot more of that, but I want to actually go through carefully what we see with a number of first order circuits. In particular, what do we see with the classic sort of RC circuit that has sort of a low pass behavior like we might see here? And what would a high pass behavior look like, a circuit something like this? Now, what's interesting is that, in both cases we're going to define a time constant RC, and you've probably seen this kind of analysis where you could do that. And what we'd also imagine by solving this, and of course this one just simply looks like a resistor voltage divider. If I'm talking about this in Laplace domain, I end up getting a pretty typical transfer function h of s 1 over 1 plus s tau. That same resistor divider done with the C and the R, again, where the R will now be still a resistance. The C is going to be a resistance of 1 over SC, will give me this transfer function h of s tau over 1 plus s tau. So you get both of these two forms, and they're kind of the duals of each other. And you want to think, well, how do I begin to analyze that? Well, the big way we typically measure these things is with step responses. One of the reasons is experimentally it's really easy to do a step response because it usually applies some sort of a square wave to the input and you can kind of build from there. Okay, so typical step response is going to be a 1 over s, and that in the Laplace domain. And I would get that in both cases. In both cases, when I do that, I can then figure out what my output response is in terms of s. One is going to be 1 over s of a 1 plus s tau. The other one's going to be a tau over 1 plus s tau. Again, very similar. In the lower case, it's fairly straightforward because it becomes 1 over 1 plus tau plus s. I know what that solution is immediately because that's in the tables of a 1 over a plus s. And I simply just, because the 1 over tau just sort of becomes the parameter that I need, and everything solves. And I get the solution below. In this particular case, it gets slightly more difficult, but not much. It's just a touch more algebra, where I need to be able to take this and transform it to a 1 over s and a tau over 1 plus s tau, which basically gives me the exact same form I saw underneath here. And it turns out this would be a separation I would get. Again, you can sort of create this and then sort of solve for what the appropriate structure should look like. Not too difficult to do. Sort of an algebra problem probably many of you are familiar with. And so at that point, I get these two pieces. I invert this. I get a u of t out of the 1. This gives me the e to the minus t over tau. And so again, I look at the responses and I see this e to the minus t over tau kind of behavior. So this tau time constant is sort of the fundamental behavior. And so the question is, well, what would this look like? Well, if I look at it for the high pass structure, and it's a high pass because we're going to be emphasizing the sort of steps, the changes, the rapid parts of it, and not the lower frequency components. So if I put a step in, I get an immediate response, and it's an instantaneous response. Basically, as I put a voltage change in V in initially, V out has to follow pretty much immediately. It has to follow immediately, and the R can't slow that process down. So I get this immediate jump, and then it curls down from there. All right, so this works out well. And you kind of see this sort of exponential decay all the way down. And you could imagine if I have particular types of R and C, I could imagine getting this time constant, which I actually can extract out of being 0.2 microseconds. Everything is great. For this response, which is a 1 minus e to the minus t over tau response, I get a step up, and I find that the output voltage starts at 0, because again, the input is at 0, so we know that at the low frequency aspect, it's all going to work just fine. And then at the step, well, because of the capacitors there, it can't quite keep up instantaneously, so it's going to take a little bit of time to reach the steady state. Okay, how long? Well, it's going to have a dynamic of 1 minus e to the minus t over tau. That tau is RC, and you can kind of look at those dynamics. Okay. And so when you look at all of this, you think, okay, I can kind of see a very nice exponential increase going towards 1 volt, which is exactly where we started. In fact, you can kind of take a look at the original response, and if you remember that the steady state is basically take S times the output voltage, and then do it as the limit goes to S equal to 0. Well, that S multiplied would divide by that S, get 1 over 1 plus s tau, that s goes to 0, it's basically 1. And you're like, oh, I get 1. Okay, everything works out. It's nice when it all works. So here's what you get when you're finished. But you go, well, that's a nice exponential, but how would I actually figure that out? And I could have done it with either of these curves, but let me do it with this case where I actually will take the output and I'll subtract the steady state from it, which means the steady state is 1. And now I'm actually going to take the absolute value to make sure that I can actually take a log of this. And so I'm actually putting this in log scale. You know, if you're in MATLAB, you're talking about semi-log y or something similar. And you go, okay, what should it look like? Well, if I plotted semi-log y, I would see all my data points, these nice circles. Basically, these are the actual data points at different points down this curve. And notice it's a straight line. In fact, I can do a straight line curve fit to this. You know, I could use polyfit and polyval to kind of create such a curve. And what's amazing is then I could actually subtract out what is tau, because the slope of this is going to be inversely proportional to tau. So I immediately get tau out of this. And so this is actually, I would argue, the most effective way to get time constant and to actually get over a grouping of points, particularly when you have data. And I'm sure many of you will get an experience to do this, either with your own data or with data that people might hand you, and you can actually go, oh, this is a good way to get time constant. It's also a good way to tell where is a system being linear, because a linear system would always have these kinds of step dynamics. Where it deviates from these step dynamics, what you realize is it's not so linear. So the whole point here was to really kind of talk through how do we look at these two circuits, and which are basically linear first order circuits, and kind of what is the time behavior that I might imagine out of these kinds of structures.